So in the last two questions, I just want to give you some examples of how we could actually use our understanding of genetics and inheritance in real life situations. So example 4 here looks at albinism, which is an inherited genetic condition that reduces the amount of melanin pigment formed in the skin, hair, and or eye. So albino pupil or organisms, it could have happened in animals as well. They just have a lot less pigments in their skin and eye and hair color than normal. And the allele for albinism is recessive. So this is a recessive genetic condition. So the situation that may happen in real life is you have two people who do not have the condition and they already have a child who has the condition. And they're expecting a second child and they want to know what is the probability that this second child will also be albino. So if you want to tackle this question, we're still going to go through our steps. So the first thing is I'm going to designate some letters to represent the alleles. It's up to you which one you want to use. So we're just going to say that the capital A, which is the dominant, this is for normal skin color or hair color without the condition. Not saying that albino people are not normal. Let's just go capital A is with melanin, so they have the regular skin color. So this is the first allele, and the recessive allele is going to be the albino. So lowercase a is albino. Okay, so you don't have enough melanin, or without melanin, basically. Melanin is just the color pigment in your skin. So without melanin. So that's step one. Step two, I'm going to write out the phenotype and genotype of the parents. Now, this question is interesting because they don't actually tell you what the genotypes of the parents are, but I think you should be able to make a prediction. So you know that for the parents, their phenotype is so with melanin, so they have with melanin. Both parents have normal melanin pigments in their skin and hair. But the fact that they already have a child who is albino means that they must be carrier for the albino allele, because the only way that a person can have, so the child is albino, which means that the child's genotype must be lowercase a. So if you work backwards, if the child already has the condition, and if this is the genotype of the child, then each parent must have one allele for albino. And because the parents don't have the condition, they must also have one allele for the melanin as well. So the parents have to be heterozygous at this trait in order for them to have a child who has the condition. All right, once again, I'm going to do step 3 and 4 together. So basically, you're going to set up your Punnett square. I think I used the wrong color there. We're going to set up the Punnett square. So we have this. Okay, and then we're just going to write out the genotypes of the parents. So one parent's capital A lowercase a, the other's capital A lowercase a. And then I'm going to just finish the Punnett square to work out the possible genotype of the offspring. So these are the offspring genotype. So only one of these 4 genotypes is going to give you the albino trait, which is this one. This is the only one that will lead to albinism. The other 3 is going to produce a child that has regular skin, hair, pigments. So basically the first child already has this, but it doesn't mean that the second child cannot have it. So the second child, there's still a 25% chance, or 1 in 4, that the second child will also have albinism. So 25% chance, what is the probability? So 25%, let me just try to find a place to write the answer. So 25% chance that the second child would have albinism. Okay, so that's example 4. So I think if two people have are carrier for albinism, then there's always a 25% chance that their child will have the condition, which is not very high, I guess, depending on what you consider to be high. All right, I just want to point out this one thing. I saw this article, and I'm pretty sure I've seen this before when we talk about things like our redhead going extinct. And so redheadedness or having red hair or even blonde hair, these are just recessive alleles when we talk about hair colors. So redhead is a lot more rare than other like brown hair color, or in my case black. And the reason for that is because redhead is recessive. So in order for someone to show the natural red hair color, they need to have two copies of the same alleles, and the same for blonde, or which is also recessive. So redhead is like that, and then blonde. So that this doesn't mean that if just because you don't see a lot of people who have red hair doesn't mean that the allele has gone away. It just means that the allele is being carried with some other alleles for like brown hair or black hair. So you can't really see it. But no, they're not gonna go extinct. If two people with brown hair who carry the allele of a redhead, if they have a child, the child has a 25% chance of being a redhead. That's all. But if you really want to see red hair, you can also dye your hair, but there's that. So no, redhead are not going extinct. Blondes are not going extinct. The allele should still be there. It's just you can't see it, but people still carry the alleles. All right. One more thing I want to point out. This is a career that really has come about in the last 20 years with the renewed understanding of genetics, and this is called genetic counseling, and this is a job that you can go study to become, and you can become a genetic counselor who will be the pupil who counsel or have specialist knowledge in human genetics, counseling, and health communication skills, and they provide information to individuals and families about genetic conditions. So how somebody inherit a condition, who in the family may be at risk, and they also provide emotional and practical support. So if you're really interested in genetics, this is one of the jobs that you can do. And you potentially could be doing what we just did with that example. If a couple came in, they say, "Oh, I have a child with who is albino. What is the probability that my second child will also have albinism?" That kind of questions. So obviously you need to know more than year 10 science to be able to become a genetic counselor, but I'm just saying this is a job that you could do if you're really interested in this topic. So we're going to talk about a more serious example of genetic condition, which is Huntington disease. I remember when I learned genetics for the first time, this was one of the things that really made an impression on me, because it is a pretty serious disease and there is a pretty high chance of inheriting it if one of the parents already has it. So it's a progressive brain disorder that causes uncontrolled movements, emotional problems, and loss of thinking ability. And it happens gradually over time when somebody essentially loses the ability to use their brain, essentially, and they can't even walk or talk, and they become solely dependent on someone else to care for them. The thing about this disease, that symptoms usually start in a person's 30s and 40s. So by the time somebody knows that they have Huntington's disease, they tend to already have a family and already have children. And the allele, and this is the interesting thing, unlike albinism or redheadedness or blonde hair, the allele for Huntington disease is a dominant allele. So if you have one copy of this allele, you will have the condition. Not to scare anyone. So this is the kind of question that can be asked. What is the likelihood that the offspring of a Huntington's disease patient also develops the condition, given that his or her parent does not have the condition? Oh, sorry, his or her partner. Oh, by his or her partner, I mean the patient's partner. The patient's. So you have a person, and maybe her father or mother has Huntington disease, and the other parent does not. And the person wants to know, what is the chance that I will also have Huntington disease? So the first thing that you want to do is you want to assign the letters. Let me just write patient here. So first thing you want to do still is you want to assign some letters for this. So Huntington's disease is the dominant allele, so we're going to do H for Huntington, and lowercase h for just a regular brain, so without the condition. This is a pretty serious condition, and yeah, once symptoms start, it really depends on how well it is managed, but it is a pretty slow and painful deterioration of a person. Okay, and then we're going to look at the phenotype and the genotype of the parents in this case. And so one of the parents has Huntington disease. So you have the Huntington, so the phenotype is with Huntington, and the other parent does not have Huntington disease. Now this is really interesting, because if you just look at the phenotype, you actually cannot predict what the genotype of the Huntington disease patient will be. So there is actually two possibility. Either the Huntington the patient of Huntington with Huntington disease is going to have the genotype of uppercase H and lowercase h, and then the other partner has to be lowercase h, or it could be both uppercase h and then lowercase h. So if you well and truly just look at the phenotype of the patients in this case, it's actually very hard to tell. And the thing is, each of these is going to change the likelihood or probability that the child of this couple is going to also have Huntington disease. So we're going to consider both cases. So I'm going to just start with this one. So this is when the Huntington disease patient is heterozygous for the trait, and then the partner, well, the partner has to be recessive for the trait. So we're going to do our Punnett square here. Ooh, okay, so if we're going to do our Punnett square here, then we can have uppercase, let me just get the correct color. So the Huntington disease patient can either give the Huntington allele or the normal allele to the child, and the other partner could only give the normal allele. So if you look at this, then these two genotypes of the child could potentially, well, will potentially develop into Huntington disease. So from the first scenario, there is a 50% chance that a child of a Huntington disease patient will also develop Huntington disease. So there is a 50% chance that the child would have Huntington disease. So I do know for a fact that in Australia, if somebody is offspring of a Huntington disease patient, they have the option of checking their actual genetic to see if they do carry the gene and whether or not they're going to develop the condition in the future, just so that they can make decisions on whether they want to have children. And because if they do have the condition, they could potentially pass that on to their children as well, have Huntington's disease. Now, the other case is if the first parent, the Huntington disease patient, is actually homozygous for this gene. And this is actually the worst scenario out of the two, because if you draw the Punnett square out, so if you draw this out, and if you look at, let me just do this again. If you assign the alleles of the gamete, so the patient can only give the Huntington disease trait, and then you have the other. So if you look at this, there is a 100% chance that the child will also develop Huntington disease. So if the patient is homozygous for Huntington disease, then this is not good news. I mean, 50% chance also already very high, but this is 100% chance. So it's like it is certain that there is a 100% chance that the child would have the condition. However, most of the time this is quite rare. Like, in order for this to happen, both parents of this patient has to have Huntington disease, because this patient must have inherited one dominant Huntington allele from each parent, and it is quite rare for two people with Huntington disease to then meet and then have a child. So it is rarer than this case, that the child would have Huntington's disease. So to answer the question, there is either a 50% chance or a 100% chance that a child of someone with Huntington's disease will also develop the condition. Okay, so that's that. We're going to talk about part B as well. So part B is if you have two people with Huntington disease, what is the likelihood that the offspring will also develop the condition? And surprisingly, this is not necessarily 100%. So once again, we already did this. So H is Huntington and lowercase h is the normal condition. And then we're going to talk about the phenotype and the genotype again. So in this particular case, both parents have the condition. So the phenotype is both of them have Huntington. So there's Huntington and then there's Huntington. Now the genotype, there are two possible combinations of genotype here. Either they are both dominant. I don't think I even need to draw a Punnett square out for this one. If both parents are homozygous for this gene, then there is a 100% chance that the child will have the condition, that the child could have Huntington. Okay, let's try again. So that's one, but there is also a possibility that one of them is heterozygous. However, if one of them is heterozygous, it's still a 100% chance that the child will have Huntington. But the third case is if both of them, actually I think I said there are two possibilities. There are three possibilities. The third case is so you either have this, or both parents or both patients are heterozygous for this gene. And we're going to talk about the third case because the other two, pretty much 100% of the time, the child will have the condition. Okay, so let me just, not this one. Let me just draw that out again. So basically we have capital case H. So the third possible outcome is if the parents are both heterozygous for this trait, and then you have Punnett square. So I mean, I think the odds are still not very high that the patient will not have it, but it's better. Okay, so you have that. So in this case, these three genotypes will develop into Huntington. So there's a 75% chance that the child will have Huntington disease, which sounds really high. But then if I say that there is a 25% chance that the child will not have Huntington disease, some people take that chance if they think it's high enough. But if you compare with the previous cases when it's 100%, and anyway, that the child would have Huntington disease. But the thing is, this is a probability. Just because the odd is really low doesn't mean it will not happen. So just because there's only 25% chance that the child of two Huntington disease patients will not have the condition, that doesn't mean that it will never happen. So that's the thing about probability. It gives you an indication of what can happen, but it can never tell you what will actually happen. This is why, especially for serious genetic conditions, there are things like genetic engineering when you can choose. You can't do it in Australia, but it's genetic engineering and then gene therapies when you can choose which gene to pass on to the children. We'll talk about this more when we talk about evolution and artificial selection. But the reason why it is an option is because for some people, the risk is just way too high that they can't really leave it for chance. But anyway, that's the last example.